But the good news is this is the only link you need now to the end of the quarter, with one exception. The Zoom link for the final will be a brand new link, right? So the Zoom link for the final will be different, but you can use this one for time onwards. So what I want to do here is give you clues on some of the homework questions from 3D. I'll try and get through it as quick as I can so we can get started on vectors, which is what's coming next. Imagine that you are given the coordinates of 3 points, P, Q, and R, and you were being asked to find the lengths of PQ, PR, and QR. And you know how to do that, right? It's that thing called the distance formula. I won't put the details in. If this triangle is equilateral, what will be true about the length of all 3 sides?
They're equal.
Right. So they're all, I don't know what they are because it depends how big the triangle, but they will all be equal. So let's pretend that it was root 7, right? They'll all be root 7. Sometimes you're asked to prove that this triangle is isosceles. What would be true in that case? So it's not equilateral, but it is isosceles. What
2 sides are equal.
So I can imagine they give you a triangle, right? And they might say, is it right angled? Yes or no. Is it isosceles? Is it no? Is it equilateral? Yes or no, right? And you just say yes or no. This is how you would tell, right? Does that make sense? You just find the length of all 3 sides and you can get it. Now, the third and last one is if this triangle was right angled. Let me pretend numbers on it. Let's suppose that was 13, this was 12, and that was 5. Now, pay no attention to the shape of the triangle, it's just a random shape. But what would be true if it was right angled? Again, using the sides.
2 of the sides will be perpendicular.
They would, but that would involve us finding vectors, which we don't know yet, so we'd have to wait to the next section to do that, but you would be able to do it that way. But since we can only use the sides, any suggestions? For instance, I know this one is definitely right angled, even if it doesn't look like it. And I even know that the right angle would be there. You got to remember this shape is drawn in 3D, right? So it could be sloping away from it. Why do I know that that is right angled?
Because distance PQ plus distance PR is equal to distance QR.
Not quite, but you're close. At least the way you phrased it is not quite right.
That, but with some squares.
That with right. So in a non-mathematical way, isn't the big side squared the sum of the other 2 sides squared? Right? So if 13 squared is the same as 12 squared, add 5 squared, which it is in this case, you are looking at right angled. Is that what you kind of meant when you said what you said?
Yes.
Yes, so you were right in the sense that if you got that question, you'd get the answer correct, right? And we're not going into the details of that, but can you imagine that's the type of thing that you're going to be looking at? Now, they go on and they give us, try to find this next one. There's one more thing that a couple of more things I should say. P, Q, and R, and now do they use the word collinear or make a straight line? It has the same thing, but I want to make sure I use the word that they use. Ah. So the answer is going to be yes or no. So I guess you could just keep guessing. You know, if your first one's wrong, you pick the second. But we want to know how to prove this, right? How would we be able to prove that PQ are on a straight line? So I'm going to give you 2 sets of data, one of which is a straight line, and the other set of data, they are not a straight line. and maybe you can figure out how you can tell. So in this one, and in this one, the top PQR is a straight line. The second PQR, right, from different points, is not on the same straight line. How can you tell that this one, P, Q, and R are a straight line, whereas this one, P, Q, and R are not a straight line? And it's not a difficult calculation, so don't think of square roots and squaring things. Much simpler than that.
PQ plus PR equals QR.
Yeah. If P to Q, then Q to R is the same distance from the start to the finish, right? 7 add 9 is 16. So if the two small ones add up to the big one, not the squares of them, just the numbers, right? The length of the two small sides added is the length of the big one. You're looking at a straight line, right? You're looking at PQR all in the same straight line, right? Now you can switch the letters around, whatever, but that property is true, right? The two small ones should always add up to the third big one. If they do, it's a straight line. If they don't, it's not a straight line, right? The jargon is collinear, if you ever see that phrase. 3 points are collinear means they're in the straight line. And not collinear would be the second situation. Are we cool with those guys? Any questions? So if I gave you P, Q, and R coordinates, are you happy about checking equilateral, isosceles, right angled, or that they're even on the same straight line as one of the other questions? We're good? Okay. We did distance to points and distance to planes, and we did spheres and spheres cutting. Yep. And I'm pretty sure we did these, but let's just be sure. What would all the points in 3D space that had this property be? What would that be? What surface?
A sphere.
Okay, agreed. What would this middle one be?
A circle.
It'd be a circle on the floor, but what would the whole surface in 3 dimensions be? Because these are 3 dimensions we're talking about. In 2 dimensions, you're right, that is a circle. But in 3 dimensions, what does that end up looking like?
A cylinder?
It's a cylinder. What axis is it pointing in? What way does the cylinder go?
The z-axis.
Right, the z-axis. So if you were trying to draw this guy, it would be basically, wouldn't it be an infinite vertical cylinder? And the circle you're talking about would be here, and that would be on the floor, at least the XY plane, it would be a circle. What would the x equals 6 look like? And it's not a straight line in 3D space.
A plane.
It's a plane. Vertical or horizontal?
Vertical.
Passing through where?
The z-axis.
No. Passing through where? So it's vertical. It's not passing through the z-axis. The z-axis actually would be parallel to this plane.
Oh, sorry. It would be parallel to the y-axis and the z-axis, passing
Yes,
through the
I know,
x-axis.
parallel to the y-axis, vertical on the z, right? And off you go. So you could plug them in with varying degrees of success in GeoBra. Now it gives me a good point. Remember that y equals x squared 1, which I tried to draw and failed miserably on, but I did tell you it would look like this. Remember that one? It's meant to look like that. Right. Evidently, you have to call it, let me get this right. well, x squared, take away y squared, plus 0 z squared. Is that it? Try and remind,
No, you
Tina.
just have to switch the order. So instead of typing it in as y equals x squared, if you type it in as x squared equals y, for some reason the system totally does what it's supposed to.
Huh. Okay, I forgot. I thought I saw something else. Oh, it rewrites it underneath. That's what I was looking at. It rewrites it underneath. So evidently, for no apparent reason, that way round works. Go figure. Are we good? Yes? Okay, let's move on then. I got confused here. I'm in a permanent state of confusion. Here we go. 12(2) now vectors. Now we are going to have this Monday off, right? So that means that your homework will be due midnight Monday. Now, if we got a day off, I don't see any problems in pushing it. But you are going to have a lot of homework to do. So I'm warning you up front. Hopefully it's relatively easy to do. That would at least be something. So we're going to look at vectors. In particular, we're going to look at vectors in 3D space. Now, where am I going? Here we go. Not everybody has had experience of vectors to any great extent, which is a bit unfortunate. And some of you probably have had a lot of experience in vectors, right? Depends on what classes you've taken. So I'm going to kind of start off with the 2D basics and then jump right into the good stuff, the 3D. Right. Now, if you have in your 2D world X and Y, a vector starts at P, finishes at Q, and it goes like that. It's sometimes called a directed line segment. So the vector PQ is like a movement or a direction in 2D space. There is a number of different notations that we kind of have to get used to. You can describe this vector by doing PQ with an arrow above it. Have you seen that notation, those people who've seen vectors? Okay, so that's not too scary. Sometimes the vector is given a letter, normally U, V, and W are the most common ones. And so you will find that the vector is sometimes called U with a little hat above it, right? A little arrow. Have you seen that notation? Right. Same thing, it's just a different way of telling you it's a vector, right? Now, in textbooks, but only in textbooks, vectors are the same as this letter, but they write it in bold. Can you see why we don't do it when we do things in paper? It's very hard to do something in bold, because doesn't that just look like the variable u, like a single number, right? But you will see that in your textbook, right? So a bold letter means you're talking about a vector. Now, how do you describe a vector in 2D space? Well, you do it by giving its components. They're basically the numbers that tell you the movement. And there is an X component, and typically there would be a Y component. And so this vector PQ could be written like this, and this is one of the common notations. No, that is not a greater than or less than symbol. They look like it, but they're not. They're just special shaped brackets, right? And you put in 3,2. And this guy is the X component. And this number is the Y component. So a vector 3,2, right? What would that be? Well, you start anywhere in 2D space that you like, we'll call it P, and then you go 1, 2, 3 in the X direction. And then you go 2 in the Y direction. And you're going from the start to the finish, and that's PQ. Now, one of the things about vectors is when you draw a representation of a vector, for instance, this vector here, you don't need to start at the origin or anywhere in particular. For instance, according to vectors, I could do another one down here, which would qualify as the vector u, or one over here as the vector u. So there's my little u. Right, so this guy is also the vector u, and this guy is the vector u. In other words, you could draw them anywhere in 2D space. Vectors don't have the origin as their starting point. They might, but they don't need to, right? They can be drawn anywhere at any time. So far, so good. Right. Now, vectors have a direction to them, right? You're pointing up the way, in this case, left to right. And they also have some other properties. When I write that down, what am I finding about this vector?
The length.
The length. And we call this the magnitude, but it is the length, you're right. And to calculate the magnitude of a vector, you basically use Pythagoras, and it's the components squared and added. And you typically leave them alone. So you don't turn them into decimals 3.1234, right? You call it root 13. That's called the magnitude of a vector. Are we good? Nothing too out of the world. Those who've seen vectors, this is baby stuff. Those who've not, I'm taking it a little bit slower for you. Now, there are a couple of very interesting vectors. One of them is called the zero vector, and it's written like that. Or if you were looking at a textbook, it would be a bold 0. What are the components of the zero vector? What are the numbers? What are the components of the zero vector?
0.
Both zeros. And if you want to draw the zero vector, it's a dot in space. Don't you start at a point and just don't go anywhere. So the zero vector is the only vector with 0 magnitude. Would that make sense, that its length is nothing? Right. Now, there are 2 other vectors that are given special names. There's one called I in the 2D world, and there's one called J. Can anybody remember what the vector I represents, or how you would write it as a component?
Isn't
I just
it 1,
immediately-
0, the unit
It
vector?
is 1, 0, and this one is 0, 1, and this represents one movement in the X direction, and this is one movement in the Y direction. So I and J are very special vectors. They're so special, they get their own letter of the alphabet, just like the zero vector gets 0. I gets I and J gets J. And what that means is that we now have another way of writing our vector U. It can be written in terms of I and J. And sometimes vectors are written using what I call IJ notation. Not IJ, by the way, IJ. And sometimes vectors are written in their component form. These are the same vectors, right? Isn't it just two ways of telling me how the movement takes place? Still good? Got a zero vector. We've got one in the x direction called I, one in the y direction called j. Oops, that's not correct. There, a quick fix. The vector w is to the vector u. That was a good improvisation. It's called a scalar multiple. I guess I could call it its full name. Normally we just say scalar. Right, it's a scalar multiple. What are the components of this one? Well, 2u basically means twice in the u direction. Does that make sense? You just double the components. We go with that, doubling its components. Now, if you imagine that this was the original vector u, wouldn't the vector w be parallel to it, but just twice as long? And that's how it would look if you drew both of them side by side. Does that make sense, that doubling a vector doesn't change its direction? Doesn't it just double its magnitude? It makes it twice as long. And now we're going to look at, what does the negative of a vector look like? Well, which one am I got? Yeah, that'll do. The negative of a vector is written as negative whatever it is. In this case then, the negative of this vector would be -3, -2. Are you comfortable with the negative of this vector, right? Now, if you draw the original vector u, what would the vector v look like, the negative of u?
Parallel, just traveling the opposite direction.
That's exactly what it is. So it doesn't change its magnitude, doesn't it only change its direction? So the vector -u is the same length as the vector u, and you might say it's the same direction, but technically speaking, isn't one going uphill and the other going downhill? So there is a change in direction. They're parallel if you just think of them as lines, but aren't they opposites of each other if you think in the direction you travel along that line? And that's how you think of it. Are we good so far? Right, that is the end of as much as I want to do in the 2D world. A lot of what I'm going to do is equivalent in the 3D world. So now we're going to do 3D vectors. So 3D vector is like that. Can you imagine PQ is actually this pen, right? So it's popping out of the paper, right? So think of this as a 3D line, right? Not a 2D line anymore, right? It's got 3 components. And when you want to tell people what PQ is, we still use the exact same notation, which is great, right? You don't need to have new letters or symbols. And in this particular case, let's suppose that it is 3, 4, 2. So can you imagine picking a spot where my finger is, right? And then going 3 in the X, 2 in the 4 in the Y, and then 2 up. And wouldn't it be traveling like this? Can you imagine picking a spot in 3D space, going 3 in the X direction, 4 in the Y direction, 2 in the Z direction, and that's where you finish. And all the usual things that we've talked about are still true. You notice it's got component form, right? X, Y, Z. What about a scalar multiple? What would 2u look like? Well, wouldn't it just be 2 of this guy? And it would be the vector 6, 8, 4. Well, wouldn't that just look like the same guy, but twice as long, right? Great. 1 vector, 2 times the vector. What would the 0 vector look like in 3 dimensions? What would be the numbers? That should be an easy question.
Zero comma zero comma zero.
Yeah. And what about the negative of a vector? Would you agree it's -3, -4, -2? Oops, wrong bracket. There we go. And if you wanted to draw that fella, wouldn't he look just like this guy, but pointing the other way? So what you knew in 2D, can't you transfer that pretty straightforwardly into the 3D world, right? You just have an extra component. This guy is called the X component. This guy is called the Y component. And this guy here is called the Z component, right? X, Y, Z. And we have 3 vectors called I, which is 1 in the X direction. We have J, which is 1 in the Y direction. And not surprisingly, there's a third guy called K. And he is 1 in the Z direction. So I could call my vector U 3, 4, 2, but couldn't I just as equally call it 3i plus 4j plus 2k? Do you see that these are totally equivalent, right? One is the same as the other. Great. Now, the magnitude, the length of this vector. Well, when it was the 2D world, didn't you basically take the components, square them, and add them, Pythagoras? What would you like the answer to the magnitude of this vector 3, 4, 2 to be? What would you like the formula to look like? If the world was fair and everything was spinning on its axis the right way? What would the magnitude of
4 squared plus 2 squared?
Isn't it nice when math does what it should do and doesn't say, no, that's only 2D, and 3D it's messier, right? You have to do blah, blah, blah. No, isn't that clean? And again, don't worry about 9 and 25, 29. Leave it as the square root of 29. The only change to that rule would be if it was the square root of 36, wouldn't you call it 6? And if it was the square root of 20, you'd call it 2 root 5, right? But normally you just leave the square root alone if that's not the case. What we did in 2D and what we've done in 3D, would you agree that the transfer has been pretty straightforward? Right? You can do 3 dimensions what you can do in 2. I wish we could do this, but we can't because we don't have time. But I want to just talk about it for a microsecond kind of thing, because it's just so fun. Once we have figured out what 3-dimensional vectors look like.
Can I see the last little bit, that other paper?
Can't you do 4-dimensional vectors? Great. And can't you find the magnitude? Right. And the magnitude of a 4th-dimensional vector? 16, 17, 21, 46. And isn't the 0 vector in 4 dimensions? That guy. And can't you do scalar multiples and negatives and anything else you could do with 3? Can't you do it with 4? Wait a minute, can't you do it with 44 dimensional vectors if you really had a reason to? What that tells us is that the concept of vectors transfers into many dimensions in a pretty straightforward way. Would you agree? It's pretty easy to write a vector in 4 dimensions, even if you can never in your ever imagination ever visualize it, right? Kira, we saw a really lovely hypercube video, didn't we? And a hypersphere vector, right? Those would make your head hurt, but they're quite pretty, right? I've never seen a video on a 4th dimensional vector. I don't even know if they know how to make a video showing it, but they do exist in the math world, even if they don't exist in your world. Because a lot of people, engineers are bad at this, and they don't like to see the world in a way that can't exist to them. So if you say to an engineer, you're building a bridge, it has to be 3 dimensions, right? And things have to weigh things and forces have to point, but isn't everything 3D, right? But if you say to them, but you could do things in 4D or 5D, they're just going to switch off and say, I've never built a bridge in 4D. I'm never going to even use 4D. But some scientists actually do use dimensions beyond the ones that we do. And I think they're thinking outside the box and engineers are not. Shouldn't you be able to think in 4D at least as a fun exercise? But they don't want to, so it is what it is. So, scalar vector. A scalar is a single number like 5. A vector has a direction and a length. So a scalar is a single number, a vector is a length. Okay, cost of a theatre ticket. Is that a scalar or a vector? Cost of a movie ticket. Scalar, right? You know, $10, whatever it is. The current in a river. Scalar or a vector? The current, it is a vector because it has 40 mile an hour north, right? It has a direction to it as well. The flight path from Houston to Dallas. Scalar or a vector?
Vector.
Correct. And the population of the world.
Scalar.
Right, I've just answered question 1. Okay, so we got that one out of the way. If you can remember the answer, but there's only a couple of choices, so even in trial and error, you'll get it, right? So now we're going to look at, oh, damn it. I'm not very good today. It's meant to be a parallelogram of some sort, so there. And gonna get a guy going here, gonna get a guy going here. I'm gonna call this A, B, C, D. Right in the center is E. And then we've got vectors pointing all sorts of ways. I like to put the arrow in the middle of the line. The textbook puts the arrow right at the end, and that's kind of hard to see. So when you look at the question, this is version 2 I'm looking at, the arrow's here, but I like to put it right in the middle. It's just easier in my brain to see. So that guy's going this way, that guy's going this way, that one's going that way, this one's going that way, and that one's going That way we get a couple more vectors to do. Yeah, this one's going this way and this one's going this way. Right, so this diagram contains a lot of vectors on a parallelogram with the diagonals drawn. And here is a vector AB. And we're being asked to pick from a list another vector that's the same as AB. Remember, vectors don't care where you start. They only care that you're the same length as me and you're pointing in the same direction as me. So which one of the guys in this multitude of choices is the same as the vector AB?
Vector DC.
Agreed. Everyone happy with that? AB, DC. Right, next one. The vector DA. DA. DA is this one. Tell me who he is equal to.
CB.
Okay. If I put pens along them, would you agree those two? Right, that's the pen here is DA, the pen over here is CB. And they're the same length, which is important. What else does it have? The DE. Okay, that one might be a little bit more interesting. DE is that guy. Right, DE. Who's the guy that's the same as him?
EB.
Correct. And last but not least, let's get this question 2 out of the way. What's EA the same as?
CE.
Okay. Why is it not the same as EC? It's similar, but it's not the same as EC. Why is it not?
Because of the direction.
Yes. If anything, isn't that true? And I'm writing it 2 different ways. Would you agree? It's just whenever something's pointing in the wrong direction, don't you stick a minus in front of it and that compensates for it. Okay. Now, suppose I give you a vector P and its coordinates are 1, 2, 4, and a vector Q and its coordinates are 3, -3, 1. And I want to find the vector P to Q.
Can I see that last paper again, please? And thank you.
No problem. So I've got P is this coordinate, right? Now these are coordinates, not vectors. So P is this coordinate, Q is this coordinate. I want to find the vector from P to Q. So I'm going to call this guy XP, YP, ZP. I'm going to call this XQ, YQ, and ZQ. And it's X of Q take away X of P, comma, Y of Q take away Y of P, comma, Z of Q take away Z of P. That is the formula that you use to find the vector joining P to Q. I don't normally remember it as this formula. I remember it as second guy take away first guy. So basically you go 3 take away 1 is 2. -3 take away 2 is -5, and 1 take away 4 is -3. I find that much easier to do than formulas. Do you get what I'm saying? Second guy, take away first. Second guy, take away first. Second guy, take away first. And you have got your vector. So that's how you find a vector joining 2 points when you're given the coordinates of those 2 points. Now, the next one is a picture that looks even uglier than the last one. This is going to be my attempt at it, at least. We have A, B, C, and D. And this is question. This is number 4. And we're being asked to add 2 vectors together. And when we're finished, the answer should be a single vector that is the same as this. The way I tend to do these questions is I think of journeys. And so I'm starting at A and I'm going to B. And then B, I'm going to C. Wouldn't that same journey be the same as going from A to C? Does that make sense? So A to B and B to C. As long as these guys here match, isn't the answer you start there and you finish there? So if I gave you a whole list of movements, just being silly here. Do you notice that they nose to tail, right? What would be the final answer to this journey, this vector addition?
AD.
Where do you start and where do you finish? Wouldn't this be the scenic route? And this would be the shortcut. Now, when they put in, as they do in question C, a subtraction, we have to do a little bit of work first. The middle don't match. This says the negative of A to B, right? So we essentially subtract. What I want you to do is to turn it into an addition. And if you take this guy and you switch him round, isn't he the same as that guy? Does that make sense? A negative AB is the same as a positive BA, right? One's a negative of the other, one's the opposite of the other. Now, when I write it this way, do you see the DA is now easy to figure out? You comfortable with that one? Right. And oh, that's 2D, I can skip that. And that's some more 2D, can skip that. On to my 3D stuff. Okay. Jumping ahead to question 9, which are all 3D things. That's fine. The vector A is given as 9i take away 8j plus 7k, which I never ever like to use. I just find that much easier on the I. Plus you don't need to write as much. So even if the question starts off like that, I almost always write it down like that. And the vector B is given as 7i take away 9k. Okay, what would that vector look like in component form? 7i take away 9k. What numbers should go here? And you do need 3 numbers, even although there's only 2 things here. (7i) take away 9k. How would you write that down?
Would it be 7, 0, -9?
Do you see why I like this notation better than that notation? Because it gets kind of hard to figure out who's missing. And sometimes I forget which one's missing. Now, the whole point of this is to find certain calculations. This is our last question for today. Okay, if you want to add 2 vectors together, A and B, so in this case, 9, -8, and 7, added to 7, 0, and 9. If the world was a fair place and everything worked, what would be the obvious way to add 2 vectors together? What would you do to these 2 vectors if you wanted to combine them, add them together?
It'd be x1, xa plus xb, and then ya plus yb, and za plus zb.
Right? Nailed it. Shouldn't you just add the x's, add the y's, and add the z's, right? That's nice. Suppose it was 2a plus 3b. Well, wouldn't you double a, which is 18, negative 16, 14, and you'd add 3 times b, which is what, 21, 0, and negative 27, right? So that's 2a, and that's 3b. And if you add these together, you should get, well, 18 add 21 is what, 39. Negative 16 add 0 is still negative 16. And 14 and add that guy is negative 13. Does that make sense that any scalar multiple of vectors a and b, you just multiply them first and then add the answers at the end? Magnitude of a, we've already done that, guy. So it's simply just going to be 9 squared, negative 8 squared, add 7 squared, and I'll just say dot, 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 because I don't have time. And if you wanted to do the magnitude of this vector, wouldn't you first find the vector and then get its length, its magnitude? So in this case, you would find this guy first, and then you would do all 3 components squared and added. And sorry for keeping you 1 minute beyond your time, but I kind of wanted to get that one done. So last name for attendance. Bye-bye. I'll hang about for any question that you might have.
Can I say something totally random that I think you'll find interesting?
Go for it.
Okay, so when I was first trying to visualize vectors in more dimensions, I was doing computer graphic stuff. And so
Oh,
when
you
I
had that problem before we
Yeah.
talked about this?
Yes. So vectors are kind
Cool.
of my jam. So so what I did in order to visualize it is I made a 3-dimensional field of spheres. And so it was like a whole bunch of spheres. And then I
Right.
represented each sphere with a multi-dimensional vector. So it had X, Y, Z, red, green, blue. So what color it was in hex. So that would be
Right.
that. And then I put stuff like, you know, the 7th dimension was viscosity, and then the 8th dimension was radius, and then the 9th dimension was density, and then the 10th dimension was what time it was. So I just like picked random stuff. It could be
Oh, so
it could be
you
like
had a position.
anything.
Yeah, so you had a position and then properties.
And then properties. So then if you do a matrix calculation and you do a vector calculation, you're like, oh, okay, what does it mean if I'm like doubling the 7th, you know, term? And it's like, oh, well, the ball went from being a squishy bouncy ball, you know, super soft viscosity or something, to being a super hard ball. Okay, well, that makes sense. I can visualize that. And then, okay, it started to be, and I had alpha too. So it'd be Sifu. So that's another one besides red, green, blue, and then alpha.
Oh, well, that's interesting. But on the same vein, if you look at space, you've got a position which is 3, and then couldn't you have the temperature as your 4th dimension?
Exactly. Yeah, temperature is a really good one. So then, and then if you represent
So the
it
sun
like,
would be a really bad place for a vector, right? And
Mhm.
outer space would be, the 4th dimension would almost be 0, or negative 273.2 if you do Kelvin, right? And the sun would be like 2 billion or whatever the temperature of the sun is. But you'd have gradients away from that, you know, close to the
Exactly.
sun. Oh, that is
Then
a
all of a sudden,
cool
at
way of
least you
looking
can
at it.
visualize the calculation in some kind of way that we can wrap our heads around, because everybody, like, there's millions of properties you could choose. You can make a 47th degree vector and still be able to kind of visualize it. It would just be a building, like if you just represented it in vector format.
Oh, cool.
So,
I like
I don't
that.
know. I just thought you'd like that because, you know, hypercubes and all that. I can't help but think of it.
Okay, that's a very interesting thought process. I never thought of that way, but I like your thinking. Okay, any other questions? That was a cool piece of information. What you got for me?
Sorry.
All right.
Yeah, I was wondering if you could show me the working for that. I know we did it in class, but I did it the same way over and over, and I just kept getting it wrong. So I guessed the opposite and got it right, but I want to
Okay.
know why.
Okay. These happen to be my numbers. Do you have yours, or do you want me to just work on mine?
Mine are 0, -4, 5.
Okay, I can keep that one.
And then E is 1, -2, 3. and then F is 3, 2, -1.
Okay, so what we're going to imagine is we've got these points. So I'm going to find the distance from D to E, the distance from E to F, and the distance from D to F, right? So that's the 3 distances. Okay, and so we're going to put these guys together, right? And the 2 small ones, if they add up to the big one, means you're in a straight line. So if you imagine that this was 3 and this was 4, but the whole thing was 7, that could only happen if they were in a straight line.
Right.
So that's the argument behind it. So to get the DE, I first have to find the vector DE. And that's going to be 1 take away nothing, -2, that's that guy, and 3 take away that guy's -2. And that ends up being the square root of 9, which is 3. Now that's DE. If I now do, say, EF, 3 take away 1, that guy take away that guy, and that guy take away that guy, I get that. And that's 16, 16, I get 34. Actually, I'm going to keep them as square roots, I think. Nah, whole numbers are fine. And the last one was D to F, and that's going to be 3 take away 0, 2 take away that is 6, and negative would take away 1, that is 6. And square root of this guy is 36, 72, 81, which I believe is 9. Now, if you take the biggest guy, which is this one, and if you add 3 and that guy, would you agree that these 2 added are not 9? That means they're not in a straight line. Now, can we pretend, because I might have screwed it up, that the right answer was the square root of 36, which is 6, right? Just pretend that was the square root of 36 now. Now, do these 2 add up to 9? Right? 3 and 6 do add up to 9.
Yes.
So if that had happened, I know it didn't in this question, but if that had happened, they would be in the same straight line. And if it didn't happen, they'd not be in the same straight line.
Okay.
So you find the vectors and then you find the magnitude of them. So you find, pick any letter you like, DE, DEF, and then EF. Doesn't matter which ones you pick as long as you've got all 3, right?
Okay.
Every combination.
Okay, that makes sense.